Hello students, in today's session let us learn about an interesting topic, push down automata. In short, it is called as PDA. In order to understand the need of PDA, it is better to know the drawbacks of finite automata, that is FA. Everybody knows that a finite automata is a simple automata designed for many languages, but we can observe from the structure of FAs that it does not have memory to store the symbols scanned from the input string and being in any state. It will not tell which are the symbols scanned to reach that particular state. This would not give an exact picture about which symbols are already and which symbols are yet to scan. As you can see here, in this DFA, it can be observed that there are two states Q 0 and Q 1. From the start state Q 0, there are two transitions, one to the state Q 0 itself with the input symbol 0 and another transition to the state Q 1. With the input symbol 1, once the automata reaches the state Q 1, it cannot say whether it has reached that state after accepting single 1 or series of zeros followed by a single 1, but the automata is in final state. The final state is Q 1. Continuing the observation, the self transition in the state Q 1 with the input symbol 0 says there is a transition to the same state. Here FA cannot remember whether it has accepted single 0 or more number of zeros. It can only say that automata is in state Q 1 and it is final state. This is main drawback of a finite automata. Because of this drawback, finite automata cannot be used to design solutions for many problems. Some of the problems include L equals a power n b power n such that n greater than or equal to 0, L equals a power n b power 2 n such that n greater than or equal to 0, L equals WWR where WR is reverse of W. To overcome these drawbacks of finite automata, another type of automata called as push down automata, in short called as PDA, can be used. Let us start with definition of PDA followed by a design of PDA for a specific language given. PDA uses a stack as a memory device to store the symbols scanned. We know stack can store symbols. Push is an operation used to add a symbol onto stack and pop is an operation used to remove an element from stack. So, PDA uses same operations push and pop for designing. Transitions are written for both push and pop operations. PDA also uses replace operation to replace one symbol on the stack top from another symbol. The formal definition of PDA is defined as a set of 7 tuples, that is, a PDA denoted by M is equal to Q, sigma, tau, delta, Q 0, Z and F, where Q is finite set of internal states of a PDA, sigma is finite set of input symbols on which PDA is designed, tau is set of stack symbols, delta is a transition function defined for accepting a specified language, Q 0 is an initial state of a PDA, F is set of final states or accepting states. An empty stack is indicated with Z 0. The transition function delta is very much important in PDA. It is defined as a mapping with Q, sigma and tau, that is, in any state Q for an input symbol from sigma with the symbol on stack top from tau, there is a transition to the state Q with update in stack. It can be represented as delta of Q A Z equals Q Z. Let us go through different variations of or types of transitions. Type 1, Q 0 A Z equals Q 0 A Z is a push transition. It says in a state Q 0 with the input symbol A when stack has Z, that is an initial condition, there is a transition to the same state Q 0 and a scanned symbol is A is pushed onto the stack. Type 2, Q 0 AA equals Q 1 A is a replace transition. It says in a state Q 0 with the input symbol A when stack top has A, there is a transition to the state Q 1 and the symbol on the stack top, that is A, is replaced by an uppercase A. Type 3, Q naught A B equals Q naught epsilon is a pop transition, wherein a state Q naught scanning the input symbol A with the stack top as B. There is a transition to the state Q naught and stack top is replaced with epsilon. Replacing any symbol on top of the stack by epsilon means removing a symbol from the stack, and it is called popping a symbol from stack. At any point of time, we can know the instance of a PDA. This is given by instantaneous description of PDA. In short, it is called as ID of a PDA. An ID of a PDA is a triple Q, sigma, tau, where ID contains the state of a PDA, symbols yet to scan from input string, and updation shown on the stack. The ID is required to verify the strings after designing. That was a brief introduction about PDA. Now, let us solve or design a simple PDA. This is a PDA to accept the language L equals a power n b power n such that n greater than or equal to 0. To design a PDA for this language, first we have to analyze how it is designed. For that, need to list the strings accepted by Automata. Some of the strings accepted by this Automata are AB, AA, BB, AAA, BBB and so on. That is, PDA should accept n number of A's followed by n number of B's, where n value may vary. As there is a stack to store symbols and the strings has to start with series of A's and then followed by series of B's, when A's are scanned, they are pushed onto the stack, and when first B is encountered, it means there are no more A's. Now, we have to start matching B onto the stack top symbol A. So, when B is encountered, the symbol on the stack top A is popped. From then, for every occurrences of B in the input string, symbol A is popped from the stack. If there are any more A's on stack and no more B's, then string is rejected. Similarly, if there are no A's on stack and there are more B's in input string, the string is rejected. Now, transitions has to be written for every input symbol scanned and depending on the symbol on the stack top. Since in the given language the value of n greater than or equal to 0, PDA should also accept epsilon. A transition is required for this as well. The transition are as follows: delta of Q naught AZ equals Q naught AZ, delta of Q naught AA equals Q naught AA, delta of Q naught BA equals Q1 epsilon, delta of Q1 BA equals Q1 epsilon, delta of Q1 epsilon Z equals Q2 Z, delta of Q naught epsilon Z equals Q2 Z. Once these transitions are written, next step is to write a diagrammatic way for the same. At the end, we have to write ID of a PDA to show the acceptance of any string, that is, Q naught AA BB Z naught gives to Q naught ABB AZ naught, Q naught BB AZ naught, Q1 B Z naught, Q1 epsilon Z naught, Q2 epsilon Z naught. This is about introduction and definition of PDA, a problem solved using PDA. Similarly, we can solve many problems using PDA. Hope you have got a good insight on PDA. Until we meet again, thank you, bye.